A very good day to examiner, viewers, and my friend. I'm Zheng Chuan, and I am honored to join the MJIT Final Years Project Symposium. The title of my FYP is 3D CFD Simulation on a Vortex-Induced Vibration of a Cylinder, and my supervisor is Dr. Li Kui. So let me explain what is the vortex. So vortex is actually the region of fluid which is rotating around an axis, and the vortex will be shattered when the fluid is flowing through the obstacle or the cylinder. So when the obstacle of the cylinder is suspended using the spring and mass damper, the vortex will cause the vibration, and this natural phenomenon is known as vortex-induced vibration, or VIV. So now let me talk about the importance of study. The vortex-induced vibration is regarded as the main reason to cause the fatigue of the offshore structure, like the underwater pipeline and the riser of the oil rig, especially on the suspended oil rig. Therefore, it's important for us to deepen the research of the vortex-induced vibration so that we have understand more of it, and we can think of the method to prevent it, to prevent the fatigue of the material. So now I'll explain why the simulation is needed. So when the computer technology is quite limited, the scientists have to conduct an experiment to study the VIV. At the wind tunnel, for example, this is the wind tunnel test for the Burj Khalifa, and for marine structure, the experiment of VIV will be conducted at the fast flow facility. However, the experiment is too costly and time consuming. Therefore, the simulation is needed. But the simulation, there's some challenges also. So the problem statement of this research is there are many simulation results still cannot duplicate the trend or experimental result, and the VIV is a complex natural phenomenon to be simulated. So the objective of this research is to identify the appropriate VIV simulation setting for fixed cylinder based on transient time model in 3D mode, and to simulate the VIV of a moving cylinder. So let me talk about the scope of study. So at first, the simulation will be conducted using a single cylinder and will be in 3D mode. And the simulation will also be conducted in transient time model. So the simulation will be conducted by using a fixed cylinder and a moving cylinder. So the main parameter to be studied by a fixed cylinder is drag coefficient and the contour of vorticity. And the main parameter to be studied for the moving cylinder is the amplitude of vibration. So let me talk about software and algorithm applied in this research. So the software I'm using is known as ANSYS Fluent, which is the simulation software to simulate the fluid dynamic. And the algorithm I'm using is K omega SST. K omega SST is actually an algorithm of Reynolds-Everest-Navier-Stokes equation, which also known as the RNS. And the mechanism of RNS is as shown as the graph at the right hand side. So the F in the graph actually the uneven or unsteady turbulence variable, and the mean of S is showing that the variable is average. So in RNS, the variable will be average before it is processed for the simulation. And now I'll explain the reason the INS is chosen and comparison of INS with other algorithms. So at first I will talk about the last AD simulation. So as shown as this graph, the last AD simulation will convert the unsteady turbulence variable to the few smoother curve before it's pre-processed or before it's processed for the simulation. And then the next algorithm I'll talk about is the direct numerical simulation. So the mechanism of this simulation or this algorithm is as shown as the picture in the right hand side. We show that the turbulence variable is not pre-processed before it is used for the simulation. So in conclusion, the advantage of the INSS is it will consume less computational power than LES and DNS because the INS is only using the mean value of the turbulence variable for the simulation. So now let me talk about methodology of this research. So during the simulation, the cylinder will be positioned for around 10 diameter from the inlet and from the wall or the symmetry. And the cylinder will also be positioned for 20 diameter from the outlet to create the boundary effect. So for fixed cylinder, we will be validated using the simulation data from EN1 2017 and the experimental result from the SUI 1983. And for the moving cylinder, it will be validated using the experimental result from the Zheng 1968. So now let me explain the setting for simulation. So the simulation model is 3D cylinder and the diameter of cylinder is set to be 1 meter. The turbulence model algorithm is K omega SST and the pressure velocity coupling model is simple. Now I will be explaining the meshing used in this simulation. So for fixed cylinder, the mesh I use is unstructured mesh. However, for moving cylinder, I use the structured mesh. The aim of using structured mesh is to ensure that the Y plus is always the same when the mesh is moving according to the effect of moving cylinder. So now I'll explain the contour vorticity of fixed cylinder. So the range of Reynolds number tested for fixed cylinder is from 45,000 to 890,000. So at first, when the Reynolds number is around 6800 and in the subcritical region, the shape of the vortex is 2p. However, when the Reynolds number is 342,000, is at the critical region and the shape is 2s. And when the Reynolds number is around 735,000, it's at the supercritical region and there is no obvious shape of vortex form. So now we're explaining the moving cylinder simulation. So for example, this is the contour of turbulent kinetic energy when the reduced velocity VR is equal to 6. And the contour of turbulent kinetic energy is also the method to display the contour of vorticity. So now I'll be talking about the plot of the result. So for the fixed cylinder, the plot of drag coefficients against logarithm of Reynolds number is plotted, and the result is compared against the SUI 1983 experimental result and the simulation result by EN1 2017. For the moving cylinder, the graph of amplitude of vibration against reduced velocity is plotted, and the result is compared against the Zheng 1968. So from the plot of result by fixed cylinder, we can see that the trend of current study cannot duplicate the trend of experimental result of SUI 1983. So usually for the experimental result, for example, from the experimental result of Yao et al. And various scientists, the trend of experimental result will be consisted of subcritical regime, critical regime, and supercritical regime. So in conclusion, for the simulation on fixed cylinder, the plot of drag coefficient do not duplicate the trend of experimental result of SWE 1983, which show the critical, subcritical, and supercritical region. However, it does duplicate the trend of simulation result by Yi and 1 2017, which is showing the reducing drag coefficient when Reynolds number is increasing. And for moving cylinder, the amplitude of vibration is almost in agreement with the Feng 1968 when the reduced velocity VR is between 6 to 8. And this is the reference I use when I'm drafting the content of this slide. And at last, I want to express my gratitude toward my supervisor, examiner, and my friend. And thank you.